The left and middle parts of this equation describe ellipses. We'll call the one on the left ellipse 1 and the one on the right ellipse 2, and we'll have a brief review of the properties of ellipses. Let's consider this equation for a standard ellipse that's centered at the origin. When y is 0, x is equal to plus or minus a. When x is 0, y is equal to plus or minus b. So our axes have length 2a and 2b. We're often interested in the location of the foci of an ellipse and the relationship between a, b, and c. If p is this point that's on the ellipse at a, 0, then by definition, the sum of the distances from p to the two foci is a constant, and here we can find the distance from p to f1 is a plus c, and the distance from p to f2 is a minus c. So that constant is 2 times a. If q is up top with coordinates 0, b, and it's on the ellipse, we have that the sum of the distances from q to the two foci is also equal to 2a. This distance is the square root of b squared plus c squared. So on the left-hand side of this equation, we have 2 times the square root, b squared plus c squared, and it's equal to 2a. We'll divide by 2 and square both sides, and we'll solve for c squared. This equation is valid where a is the major axis, that is, a is greater than b. Let's return to ellipse 1. In ellipse 1, since a squared is greater than a squared minus 16, we have that c squared is equal to a squared minus 16, which means our foci are 4 to the left and 4 to the right of the center. The problem asks to minimize a plus b in these equations. A and b roughly determine the size of our ellipses, so if we want to minimize a plus b, we want these ellipses to be as small as possible, but still intersect each other. So we'd like the intersection of our two ellipses to be 1 point, or tangent to each other. So we're going to try to find a single point P that is on ellipse 1 and on ellipse 2. This means that P satisfies the equation for the distances from the two foci of ellipse 1. That sum is equal to 2a. Similarly for ellipse 2, this distance is 2b. Let's add these two equations. And on the right-hand side, we'll get 2 times the quantity that we're looking to minimize. If we look at the sum of PF1 and PG1, and we want to minimize this sum in order to minimize a plus b, this reminds us of triangle inequality, the triangle formed by P, F1, and G1. This is going to be greater than or equal to the length of the third side of our triangle, F1, G1. And we have equality when P is on that line segment F1, G1. And similarly for the other 3 points. Let's draw our 2 tangent ellipses. One is centered at the origin, and the other one is centered at 2011, and its major axis goes up and down. Here's F1 and F2, G1 and G2. So P is on these 2 line segments where our 2 ellipses are tangent to each other. Let's take our earlier equation and solve for a plus b. This expression on the right is greater than or equal to 1/2 the distance from F1 to G1 plus F2 to G2. That's just the distance between these 2 pairs of foci. F1 is at 4, 0, F2 is at positive 4, 0. We have 2010 here and 2012 up here. When we draw in these right triangles, the distance from G1 to Q is 10, and F1 to Q is 24. We see a Pythagorean triple here. And then the other right triangle from F2, G2, and down to Q. This height is 12. This distance is 20 minus 4, or 16. And we have another Pythagorean triple, so the distance is 20. We'll plug these in. We have 26 and 20, and our answer is 23. If you'd like me to solve any other AIME or AMC problems, please leave them in the comments.